Hello everyone, welcome back to the second part of a YouTube presentation on fast exact simulation of the first passage event of a tempered stable subordinator. This is joint work with Feng Ling and Alexander Mijatovic from the University of Warwick and the Alan Turing Institute. This work was funded by EPSRC. So on the first part of the presentation, we give a short overview of the algorithm and how it can be used to solve numerically fractional partial differential equations as well as price certain barrier options. In this part of the presentation, we will instead give a deeper insight into how the algorithm works, what the structure is, and where the problems arise, as well as how we address them or how we circumvent them. Okay, so first of all, recall we're considering an absolutely continuous non-increasing curve B and a tempered stable subordinator S. We're interested in the first time tau, where the subordinator crosses, the value before crossing and after crossing. Okay, so these are known as undershoot and overshoot, or well, the overshoot can be recovered from these values. Okay, so the first idea is to use the Escher transform. So basically, we will start with a stable subordinator with this parametrization, where W alpha is given by this, and we will construct a random Nicotin derivative and an equivalent probability measure PQ, under which S will be a tempered stable subordinator. So the Chorlton parametrization makes it so that the Laplace transform has this simple form. Okay, that's it. But theta is arbitrary, so it really spans all this class. Okay, so the idea will be to basically reduce the problem to simulation under the stable law and then doing some kind of accept reject. Okay, more specifically, for a given event B, if you can sample the event B as well as the marginal ST and then an independent exponential variable E, the probability of B under PQ is the same as the probability of B under P when you condition on an exponential variable exceeding Q times ST. That is, we can sample the event B as well as ST jointly, and then an independent E, and do this iteratively, repeatedly, until the exponential exceeds Q times ST. And then we accept the event B, right? And note that this also works for conditional probabilities. So for example, if we have some event of positive probability C, the conditional event can also be written like this, right? So this is really nice. And unfortunately, we cannot directly do this for a random time tau B. That is, we cannot just simply plug in here T equals tau B and hope it works, right? But we can make it work for any deterministic time. So the first tool would be to introduce some arbitrary time grid with a T star, yes? So what we will do is get successive increments of the subordinator, and until we find the batch, so the grid bit where the crossing occurs, right? And when we detect crossing, we will then sample the crossing time, value, and undershoot, right? Okay, so we could not simply do in this Escher transform technique, we could not simply put a random time, but we can always put T star. So conditional on this event, on the crossing occurring, since we have a stopping time, this is adapted, so it's all nice, right? I mean, we will be able to apply precisely formula 4.2. And after optimizing for T star, you only need to set T star to this value, initialize this variable, capital T and U as this, and get increments of the tempered stable law while you remain below the curve, right? And as soon as you exceed the curve, you will then detect that a crossing has occurred. So you now need to do a simulation of the triple, conditioning on the crossing occurring under the stable law, then sample the missing bit of the stable increment that will take me from time tau B all the way to time T star, an independent exponential variable, and accept the sample when the exponential exceeds Q times W plus V. So W comes from this bit of the increment and small v comes from this bit of the increment, yeah? So both of them together give me ST star. And once this is all done, I'll just get the triple from this step and get all the accumulated time from when I was drawing the increments below the curve, and that's your sample, right? So obviously this algorithm is very simple, and it's obvious now that the missing component in how we do things really is this line 9. So it really boils down to the stable case. Okay? So first, let's analyze the complexity of the previous algorithm. It turns out to have this kind of form. And the ugliest part here is the exponential dependence in Q be 0 and alpha. Alpha close to 0. So this is off-putting. Of course, kind of common in this kind of techniques when you use Escher transform, but there's also standard ways of dealing with this problem and reducing the complexity. All we have to do is play with the B. So we can do consecutive crossings of smaller functions, right? So cap B0 at some fixed capital R, and do consecutive crossings until we cross the actual barrier function B, right? So that is, we will check when we cross either R or B, the minimum of both. Once this happens, we check for the next time it crosses, and so on, right? Each of these events happens much more, each of these simulations are very, very fast. And you just need to do it many times, but still the complexity is not exponential now, it's just linear, right? So now complexity is linear in Q, in B0, at most cubic in alpha for alpha close to 1, at most quadratic plus log near 0, and of course logarithmic in the number of precision bits. Okay, so it's all polynomial basically, and it's in practice very fast and much better than what the upper bound would suggest. Okay, so how do we do the simulation for the stable case? It basically has 3 steps, okay? Which correspond to the 3 bits in the proposition to G. The first step is simulating the crossing time. So the crossing time has the same law as a given function evaluated at the stable variable at time 1, so stable subordinator at time 1. Okay, so what is this function? Well, you take the barrier bt, which may or may not hit 0, and if it hits 0, it's only defined up to tb. You multiply by t2 minus 1 over alpha, so now this will be a strictly decreasing function, absolutely continuous still, and it will have an inverse b minus 1, yes? And all we need to do is evaluate b minus 1 at a stable subordinate at time 1, and this will give me the crossing time, right? This is not so surprising, and really the only technical bit here is, the only tool in the proof is using the rescaling property of stable subordinators. So now, second step, we need to determine whether the crossing occurred continuously or not. So continuously means creeping, right? It means that the process is exactly equal to the barrier at the time of crossing. And it turns out that this probability is very simple, and the only dependence in alpha is here. And if the crossing occurs continuously, then we simply return the time tau b, the barrier at time tau b, and the barrier at time tau b, right? Things occurred continuously and there was no jump. If there is no creeping, that means that the crossing occurred via a jump, and then here comes the hard part, right? We need to simulate both the undershoot and the overshoot. So both densities are very explicit. In fact, given the undershoot u, the overshoot is simply a power law. So it's also very easy to simulate. Now, unfortunately, the undershoot has an explicit but very complicated density. So the dependence in u is only here. And you can see that somehow, and gt is the density of the stable subordinator at time t and spatial value u. So this is some kind of, if you integrate this, you would get a fractional derivative of the stable density, right? The fractional derivative at b of t. So this is a strange looking function. It doesn't look so ugly, but turns out to be much harder than it seems, because the density, although explicit itself, is often written in terms of integrals or infinite series expansion, right? So it's not entirely easy. Now the second bit is that this thing is unbounded and very tricky to simulate from. In fact, Chi was the first one to use this representation to do a simulation algorithm. And although the algorithm works, in practice it has an infinite expected running time. The reason for this is that at this step, what he suggested was, okay, this density I can sample from, because it's just a beta, and I can accept or reject with this guy, right? Because the subordinator density is a bounded function. Now, unfortunately, for a given t, for a given fixed parameters, This works well. It's just rejection sampling. It's a geometric variable, essentially, right? But in general, when time t is random with this law, then complications arise, and the acceptance probability can become really, really tiny. Yes, especially because time t at all can be very heavy-tailed, and then this probability can just get to very, very small values. So, in fact, this is what turns out to make a cheese algorithm have infinite expected running time, or one of the things, right? So doing this simulation efficiently is not at all easy, and it's in some sense the main technical contribution of our paper. Okay, so first, let me give you the algorithm, and you can check for yourselves that this is really how it works. You simply sample the crossing time, you toss your coin to determine whether you had a crossing or not, a creeping or not. If there's no creeping, sample the undershoot, and then sample overshoot, and see, the overshoot is really easy. So now we need to understand how to do the undershoot. Okay, but before we go there, let me show you that the theoretical bounds and the complexity do actually work. Numerical simulations show that indeed the expected running time per 10,000 samples of t divided by log alpha is a bounded function. It seems to converge to something below 1, which is fine because our bound only claims to be log of alpha for alpha small. Look at the time grid, this is like 0.001, so this is practice most cases, right? Now for alpha going to 1, you also see the same behavior. Now this is log of the expected runtime divided by log of 1 minus alpha, and according to our bound, this should be bounded by 3. And indeed, it actually seems to converge to approximately 0.2, which is completely fine. So, okay, let's go back to sampling the undershoot. How are we going to do this? First, at a high level, let me give you some words, and then later we'll get into a bit of formula, just a bit. Okay, so the density of S to minus is explicit in some form, in a semi-analytic version, but it is not great for direct, efficient, accept-reject methods. So the main strategy will be to break up the domain into regions, depending on the value of the random parameters, and do either a mix of accept-reject methods or apply the Roy's algorithm for log concave densities. So the Roy's algorithm turns out to be crucial for our algorithm to work, because regardless of the scaling constant in the density, it just has constant universally bounded complexity, right? So the acceptance probability is bounded by 1/5 for any log concave density. This is completely impressive and very necessary for our algorithm to work efficiently. In fact, it's used precisely when the density has super exponentially small values. So what I mean by super exponentially, you can imagine the function e to minus 1 over x for x close to 0, right? You can see that this density decays very, very sharply, and it's easy to get a bounding function. It's hard to get a bounding function for which the acceptance probability is large, right? Particularly if you don't even know the normalizing constant. And even that may be hard to compute efficiently because the values are tremendously small. Okay, so let me just tell you that our algorithms employ a mixture of both binary search, like the Roy's algorithm has such a thing for a random parameter that will appear, well, a parameter that appears in the algorithm, and in our case will be random because all the parameters are random. And this is possibly followed by Newton-Raphson, and when we do this, we are always very rigorous about verifying that the assumptions that ensure quadratic convergence hold. And the second component is accept-reject. The Roy's algorithm is in fact an accept-reject method, and of course we also find ourselves some nice bounding functions that will have an appropriate acceptance probability. And for both components, we do a very careful complexity analysis. So it is very important and crucial to get a control in the running time, especially because these parameters are often very random and can result in infinite expected running time. In fact, as we said before, this is why Chi's algorithm has infinite expected runtime. It has an accept-reject step, which in principle is good, but the problem is that the acceptance probability is random and can get to very small values. Okay, so now with a little bit more formulae, what we're going to do is this, okay? So first, we realize that the stable density can be written as in an integral form. If we disintegrate it, we essentially have now a bivariate problem, and we can transform one of the coordinates to get this kind of density, okay, or joint density. Now, here the function sigma alpha is explicit. It's in fact a quotient of sine functions to some powers, but the explicit form is not really illustrative or helpful in any way because it's really unmanageable. Instead, the only thing we will use about it is the fact that it is convex. Okay, and then the density has this form, and all we need to do is sample this pair and return the first coordinate transformed in this form. Okay, now here, as you can see in this olive color, these parameters is random and will be everywhere in this slide. So the next step is to find a mixture of nicer densities from which we can sample. So you can see that this one is not really nice in x even. It looks like an exponential factor, but then also this ugly function. And even for y, that's also not very nice because of this convex but otherwise unmanageable function sigma. Instead, we find a mixture, psi tilde, which dominates psi in this form. And psi tilde is a mixture of psi 1 and psi 2. Psi 1 is really essentially an exponential variable in x with random rate sigma. So for example, if we integrate x out to get the marginal in y, we will see that it's a log concave density. So we can simply directly apply de Vroij's algorithm. And once we have the sigma, the y variable, it's simply an exponential with this rate for x. So this is obvious. And now psi 2 follows a similar logic, but in this case we will have a gamma density. Okay? So again, when we integrate x out, it is not so simple. It does not simplify this easily, but it is still something that we can break the domain apart into bits. For a big chunk, we use de Vroij's algorithm, and for when it's not log concave, we need to find explicit functions explicit densities that will bound the thing, right? As I said, psi 1 is basically de Vroij's algorithm. Psi 2 has a part of de Vroij's algorithm, and otherwise you need to break the domain, break into cases, and do very delicate analysis. The details of these analyses are found in the paper. I did not think they would fit in this presentation because it would not convey any more insight into how this works. It's just hard maths and analysis. But I hope you enjoyed the presentation and you found this algorithm useful. Bye-bye.